I'm Colin Davidson, one of the staff of the Handmade Network, bringing you a new show, Unwind, a spotlight for some of the cool things the Handmade Network community is working on. Today's our kickoffs. We've got a special show with two speakers. First up, Yasser Arguelles on compiler backend optimization, and then wrapping with Jon Lipstate on developer clarity. Each of the segments will be followed by a short Q&A, so stick around if you've got questions for a speaker. Unfortunately, Billy, the third speaker, wasn't able to make it today, but he'll be with us on a future date. So, Yasser first. He makes terrible oversalted rice, and he works on compilers. He's been fighting the LLVM dragon for as long as I've known him, proving to the world that compilers don't have to be slow. 1 second. You're good?
All right. Hello, my name is Yasser, and I work on tilde TB. I usually call it TB. People call it tilde, but essentially it is an alternative to LLVM. That's the main gist of it. And I want to talk about some optimizations that are a little bit less loved. So there's the common ones you might hear about. You have your inlining and vectorization, but then there is also the things like constant propagation, dead code elimination, and in this case, a combined form of constant propagation and and dead code elimination called sparse conditional constant propagation. And so I'm going to be talking about some of the stuff that it takes to actually implement that as a thing that your compiler can do. And so to start off, we're going to have SSA. So in SSA, what we're effectively doing is taking all of these mutable assignments and converting them into single assignments. And that's where it gets the name static single assignment. So instead of saying x equals 16 and then later on reassigning x, we actually make a new x value, which is going to represent x after the mutation. And in which case, we end up with two immutable assignments, which makes it easier to reason about what's going on. No longer do we have the problem of, is x referring to the same x as some other x in time or not? And so we run into conflicts immediately where we say, okay, what if something actually has two definitions? Like in this case, we've got x equals 16 and x equals 12. What do we do there? And the short answer is we solve this conflict with something called a phi. And these are basically mappings between a specific code path that you can code down and the value that's going to be assigned to this later code path. So essentially, when we jump to L3, this phi is going to be assigned based off of the value that came from. So in L1, we're going to take 16. In L2, we're going to take 12. And that resolves our conflict. And this is data flow at its finest. It means that we can map on to concepts like when does data actually change as opposed to when is data just a name for the result of an expression. And here's a different example with a loop. In this one, we can see we start off with 0, which 0 gets passed off into this phi. And then when we go around, we actually take this I3, and thus we have this sort of cycle here that represents the literal cyclical nature of the iterator. And there's a different way to represent this called basic block parameters. And so the idea is that these labels are representing basic blocks. They are pieces of straight line code that end off with some sort of branch or some other. They can branch at the ends, but they can't branch in the middle, and you can't enter anywhere but the top. And so you end up with these little basic blocks, these little straight line pieces of code, and we reason about these because it's far easier to reason about them than it would be not to. The same thing as SSA. The idea is that our representation of the program should be helping us solve problems. And so in this case, instead of passing around a phi node, we instead have a parameter on the basic block, in which case we pass along 0, and when we go around, we pass along +1, or I2 +1. And in TB, I actually end up doing something very similar. I do basic block parameters. Well, really, they're actually equivalent concepts. So I actually do phi nodes internally, as in the data structure looks like a phi node. But in terms of how it gets printed as a sort of basic block parameter. And so now, here's a few terms that I've thrown around. So we got SSA, static single assignment. We've got our phi nodes. They resolve weird conflicts. Basic blocks, little straight line pieces of code that enter from the top, exit from the bottom. And then basic block parameters, a different way for solving for phi nodes that is, well, equivalent. And then important thing, monotonic/monotone, these are going to be referencing forward progress. And the idea is that we've got some function, let's say we have graph goes up, graph stays going up, or graph goes down, graph stays going down. And that's going to play into one of the common patterns you're going to see in a compiler. And this is a monotone framework. The idea is basically that we start off with all of our values initialized to this so-called top value. And from there, we keep calling this f function, and it keeps producing a new value that is going to make some amount of forward progress. Either that or it's going to stop working. And the idea is then we have like this local rewriting system that's going to effectively flood fill our program with some sort of analysis. This is going to be used for different kinds of analysis, but in this case, we're going to use it for constant propagation. And so we've got our lattice over here. And the general idea is that a lattice is going to order a set of sets. And so we're going to use these sets to represent constants, and we're going to use them to represent the possible values that any sort of value can be. So like if we have an expression, there is a data type that might tell us, oh, this is an integer, and therefore it has to fit within a certain range. We can actually model the set of possible values as a real set and then do mathematics on it based off of these sets. So in this case, we've got what is called our top, we've got our bottom, and the idea is that as we run through the monotone framework, we are going to slowly move downward. So we start at the top, and from the top we have no information. The set is empty, and this is a sort of invalid state. We have no clue what's going on, and we know that we don't know. Then we have the middle state where we absolutely know it's a specific constant. So this is a set that includes one value, and in which case, this is great. We can now get some constant information out of it, and we can propagate that. And at the bottom, we have the bottom. The bottom lattice, the bottom set, is basically going to represent all possible values, which means that we don't know anything about the value. We know maybe that its data type is something, and like that tells us it's maybe between some effective range, but it's not very useful information. And there's some operations we can apply onto these sets, these lattices. And so these are the important one right now is going to be the meet function, which is effectively a union. And so the idea is like if I union something with itself, it doesn't do anything. If I do unions, they're commutative, they're also associative, and we get a bunch of these neat little things. And then if I union with a top, I also get back the same value. And the reason why is because top is basically an empty set. So if we union with an empty set, we don't get anything else. And if we union with bottom, we get bottom because bottom contains all the possible values. So anything being unioned with it will just give us all the possible values back. And then we can also talk about ordering, where we can say that certain things are on top of each other. So both of these rules are sort of indicative of the actual rule, which is that meeting something with something else can actually tell us where it's ordered in the actual, in the lattice. So now we're going to try to like let's tie that back into actual compiler-y implementation-y bits. So we got this constant propagation problem right here, where we need to take some code that's got a few conditionals, a few variables, it's got some constants in there, and we need to try to deduce some information. One path says 16, one path says 12, and then the phi node over there is going to do one of these meet functions. It's going to union both of those values and try to figure out what it can deduce from that. The problem we run into is that our previous lattice was saying that we can only represent a constant. We can either represent all values, unknown values, all values, or a constant. And this doesn't leave us much range to talk about the union between two separate constants. What do we do there? And the short answer is we're just going to have to do the conservative guess of bottom, which means that it's going to be all values since we don't know which one of them is going to be. And what we can do is, or what we end up with is the problem is we don't know that x3 is equal to 0. We don't know if it's equal or not equal to 0 because it's just the bottom. It could be, and we don't know that. And this means we're losing information. A simple way to get back some of that information is instead of representing only individual constants in our lattice, we can actually have more sets of information. So instead of doing constants, we can do ranges. And in which case, if I union the range of 16 and 12, what I get is between 16 and 12, which is a conservative guess because it means that 13 would count as one of these values that it could be, which is not necessarily true in practice, but is not untrue. And so what we get instead is now the x3 is 12 through 16, and in which case we know that it's never 0.
What are we looking at for
Thus,
time?
this branch is now dead, and because of that, because of this branch being dead, we also now know that this block is not alive, which means that we can then propagate that information along. And while we're doing the constant propagation, we are also doing the dead code elimination. And by doing these things, two passes combined, which are both mutually beneficial, dead code elimination tells us that there's less information to work with, which would have been really nice to know when you're doing constant propagation. Because every time that we hit one of these phis, we have to merge all the possible cases. If some of those are dead, then that's useless information. And so these two mutually beneficial passes can now be run together. And in this case, we take the dead branch and we rip it out. And now we're returning one specific value. It's great. And so the beautiful thing about the ranges is that ranges are just barely more information to store and to compute than it would be to deal with constants, and they can actually help out in tons of cases. So some of the really common ones are doing range checks against constants. The other ones are doing modulos and bit masks. If you do a bit mask, for instance, of like x, bit mask 63, the number has to be between 0 and 63. If I do something like dividing a number by 2, the top bit is now 0, so the total effective range has actually been chopped by half. If I do things like in Odin, for instance, if you do a shifting operation and it overflows, as in the shift amount goes greater than the bit width, what it'll do is it'll return 0, which is effectively sort of thinking of the shift as moving the values in a sliding window, as opposed to having the shift amount be something that can wrap. And because of that, what we end up with is we end up with an extra check on every shift. We can actually deduce this check away if we have a little bit of range analysis. If we can talk about the range of the shift amount, then we could say, oh, this range is always in range or always out of range, or it's always somewhere in between and we don't know. And so in this case, if I were to write a bit mask 63, I always know that the A or the bit masked value is going to be between 0 and 63, so it'll never do this overflow behavior. Thus, the check is now redundant. And then we can also do the same types of things when we're talking about pointers. We can say that there are pointers that are null, there are pointers that are non-null, and there are pointers where we don't know, and that would be the bottom type. And so we're back to our monotone frameworks, except this time I've swapped out the term lattice with type, and it's exactly the same thing over here, which is that this same concept is going to be thrown into a bunch of different things. I do hope that people look into the monotone framework stuff, because there's a bunch of patterns that come up with it. So in this case, it's being done for constant propagation. There's also like data flow analysis, where we're trying to figure out how long are values alive. So like, is a value being propagated to somebody else or not? And these are all these effective flood fill algorithms. And now we filled in what this f function is, which we didn't define before. And so in this case, the f function is going to give a type to any single node, any single instruction in our graph. And in which case, that's going to be, for the phi node, it's just going to meet union all of the different values a phi node could possibly be, which means that a phi node's possible values are just the union of all of its possible values, which sort of is just intuitively true. Now, the weirder case is actually this addition over here, because this addition says that if the if the A is a top, if the left side is a top, or the right side is a top, then we're going to return top. What we're basically saying there is that if we were to add top to something, this actually sort of violates some of the rules we mentioned earlier to do with meeting, where meeting actually works differently. The reason why addition doesn't work the same is because we don't necessarily want to reduce the type without knowing what both sides are. And so what we'll do is we will wait until both sides are resolved, which the monotone framework will guarantee at some point to happen. And this is because it keeps pushing the user. So anytime a node changes, all of its users are notified. And thus, later on, once both values are filled in, we can then deduce the minimum and maximum type of the addition. And in which case, we can get some interesting information out of it. And here's a little dumb implementation in C, where you would basically have to fill in your meet function and your construction of an integer type. And you can add as many types as you want, as long as you sort of model there being a top or bottom. Technically, they're optional in lattice theory. In terms of constant propagation, they're very, very powerful and basically necessary, because we want to talk about known unknowns and unknown unknowns. And so this is a fancier example that MSVC actually shared in 2015, back when they were originally showcasing their SSA optimizer. And the idea is that this entire function is actually deducible to not, like, none of these branches are useful, because what we can deduce is that regardless of which path is taken, the value never actually exceeds their expectation down here for the checks. So if I remember correctly, we can walk it through with a lovely marker. Oh, yeah. So we've got two x's. These two x's both meet and give us some range between 4 and 9. And now we take the two y's, they meet. They both meet and give us a range between 1 and 2. And then z, we know that the bottom bits of z are unset here, and we know that the bottom bits of z are unset here. Both ranges are not going to include the bottom, 255 bits. So we can start at 256 and then go up to whatever the max is. And that is what z is, or at least the phi of z that ends up down here. And so now when we do the math, we can figure out that the maximum range for doing x times y is going to be 18. And then times 4, can't do math, so what is that? 32? Yeah, 32. And then 4. Don't trust my math. I can't do math. Let's see. 4. That sounds about right. 72. Somebody fact check me. But essentially, once we know that, what we can say is that the maximum value of P is going to be greater than 16. Yes, that's always true. And in which case, we can actually remove this check. And then, is Q going to equal 0? The short answer is that we know that this value over here, since Z can never actually have any bits set at the very bottom, we actually know that this Q will always be equal to 0, since there is no value between 256 and the int max that is actually going to bit mask such that it gave us 0. And therefore, there is only values that will give us 0. We actually know this because of the known bits over here. Either all the 8 bits are not, or all the 8 bits at the bottom are 0 here, all the 8 bits at the bottom are 0 here, and thus we know that this over here is also 0. And therefore, we can just deduce the answer by having walk constant propagation. And one of the things they showcase is actually that they track known bits. And this is something I also do, where you also track the known ones and known zeros, such that bit operations like this tell you whether or not certain bits are set. And this is helpful for unsigned operations, whether or not you want to know about signed and unsigned. So for instance, some operations don't work nicely when they overflow, and you can do range analysis for this. But you can also check things like whether or not the known bit of like the signed bit is set. If the signed bit is unset in 2 numbers, what can you say about that, for instance? And so, jump back over here.
Sure.
Wow, we got a bunch of shitty diagrams over it, but essentially these are the terms that we've got through here. So we've got, so in terms of added terms, we've got the monotone frameworks, which are basically these little flood fill algorithms.
Sure I'm taking notes.
We've got the constant propagation, which is just folding but cooler.
I'm sure people want to go
lattice, which is our nice ordered lattice of sets, of ordered sets, or partially ordered sets, really, because you might have noticed earlier that the number 1 is actually next to the number 0, for instance. And so you'd end up with a top up here, a bottom up here, and then a bunch of different types over here, and so on and so forth. But these would actually be next to each other. And so comparing ordering between a 0 and a 1 would actually just like give you a bottom, because you in fact can't tell which one is bigger than the other, because what we're measuring here with the ordering is not like which numbers are greater or less than each other. We're actually measuring how much information we actually hold. And so this set has no information. It's an empty set. This is a set of 1, and this is a set of infinite, or all the values. And yeah, there you go. Now let me take this down so I can do Q&A stuff. There you go. Yeah. Yep, I can hear. All right.
Yes. Right. Okay. My apologies. Mild technical issues. It is the first stream. We're all good. So, looks like we got a couple of questions. Looks like Strigger has a question about, well, if Z ends 15 is 0, can you see a min-max range of 2 to 6 minus int max? I think there was some...
Sorry, it wasn't an int max, or it wasn't a minus, it was a range.
Okay.
But the idea is also that we track known bits.
Right. Cool.
So if we had known bits of, if we have these two operations, x and 0x 55, if our ranges track both like effective integer ranges, so one continuous interval, and also known bits, so the zeros are set, we know, well, actually, sorry, it was 0 and 0. And so we know actually that these bits are unset, which means that any operation that actually uses those, like our later, let me rewrite that, whoops. Like our later 0x F, then we know that this operation is obviously going to give us 0. And then the same thing was true of shifting up by 8. That would also give us 8 known 0 bits at the bottom.
You're probably hearing... so Yasser is upstairs. So you might be hearing a little bit of Yasser background noise.
That's funny.
Well, there's a lovely blanky Easter egg in the back there. That's a great question. So what would you change about TB if you were to start from scratch tomorrow?
Probably nothing. I've refactored so many times that I basically have.
Sweet.
So
what's next on the TB
that's what I'm
roadmap?
bought in. On the TB roadmap, currently doing a refactor. I've been at like 2 weeks worth of. Well, refactor is the wrong term. I'm adding ARM support. I'm basically taking a bunch of components that are used to generate like machine code for different targets, like the scheduler. So we got like I can't write. You got the scheduler. We've got RA for register allocation. And we've got 2 schedulers. We've got the global and local ones. So the global scheduler tells me which basic blocks to actually put values into. And the local scheduler tells me within those basic blocks, what do the values order as. And then register allocation just solves the problem of I've got a limited number of registers. How do I figure out which registers deserve to have these values and so on and so forth? And also the spilling problems. So we run out of registers. What do we do? And so like these components are all something I could generalize outside of the actual code generation of any single target. And so I've been doing that so I can have a more general setup for adding new targets.
What kind of info is in that? So a question from Ben. What kind of info is in that lattice again? Is it an info about a particular value, or is it all of them?
So that's the thing. It represents a set. In terms of how you set it up in memory, you're going to have some limited version of what a set is. It's going to be conservative because we don't want to store a literal array of all integers. And so in my case, I basically do a min, a max, both being inclusive, and then known zeros and known ones. And from there, these 4 values give me my integer range. And so you're going to have yourself do a little tag union because integers aren't the only type you have. So this will represent your int types, for instance. You might have pointer types, in which case you can have different kinds of pointers. So for instance, you could have, I actually don't do this as a tag. What I instead do is we have like null, we have pointer non-null. And these are the only things I track for pointers right now, which is going to expand eventually. And so the idea would be that you either are the bottom type, which means you could be either null or non-null, or you are the top type, which means we don't know yet, or you are a null pointer or non-null pointer. And if a null pointer and a non-null pointer meet, then that means that the value could be either null or non-null, which just means a bottom type again. And so stick these all into your little lovely tagged union, and that's the values in your in-memory lattice. As long as you implement the meet function and the rest of the juice around it, that's a lattice.
How does that work with floating point?
So you can do floating point. I don't do like ranges for floating point because floating point gets too messy for that kind of stuff. So instead you just do float, and then you would do your single constant. And in which case we have one of these 1-layer lattices. So it'd be top over there, bottom over there, and then all possible float values. So let's say 0.1 over there, 0.2, etc. And in which case, if you do 2 floating point operations that are both constant, you'll get folding. But the reason why you have to be more conservative about floats is because floats don't have nice properties in terms of like commutativity, or actually, sorry, commutativity is a property that they do have, but they don't have properties like nice associativity. And so you don't really want to be messing around with float optimizations unless you're doing like fast mathy stuff, which I don't really do.
Sweet. Could you store whether it's nan?
Yes, I can. And so in which case you would do something pretty simple. The same thing as the pointer null and non-null, where you could just have a nan over here. And that's it. Or you could just store a constant nan. Depends on what you actually want to encode when you say nan. So this is one of the weird details. There are many different nans. And so ideally you are encoding which nan it is. But you can also talk about nan in the abstract sense, where you say there is one NAND that my language supports, or one set of NANDs that my language supports, and the other NANDs are reserved for other stuff. So for instance, if you're doing things like NAND tagging, you might want to say, these are the NANDs for like floating point NAND arithmetic, and then there is NANDs for I'm tagging NANDs.
Awesome. Well, thank you. This has been really great, Yasser. I appreciate it.
Thanks.
1 second. All right. So next up, we've got Jon. And Jon is new to the community, but he's made a big splash writing a package manager for Odin. He's an engineering lead moving into software pretty recently, bringing us a fresh new take and perspective on communicating clearly and sharing ideas with your team.
I wanted to talk about clarity today. I think it's an interesting topic and it has a lot of benefits. I do think it is a path to accelerating your competence. And it's a difficult topic because it's very nebulous, right? In this crowd, we can absolutely measure millisecond, microsecond performance. And so there's a very objective, how fast is your code? How well does it perform? But if it's not clear, then only you can use it, you and the computer. And so if you're working by yourself or in a small team, the cost of lack of clarity is probably pretty tolerable, but maybe it can be annoying. If you can stumble your way through a problem and you don't necessarily understand it, and end at the finish line with a complete, functional, even successful product. And technically, this can be done in larger teams too, but when it goes wrong, the results are either a spectacular implosion or it could be a really muddled and painful slog. I think we see this at any typical large company. As an example, if I want to go in to use a library for something, I'll go peruse the code for a bit. Very few libraries can survive even this cursory scrutiny. Under the hood, they're just often a big tangled mess. More often than not, I have a serious debate with myself on if it's worth trying to understand their library or just write my own from scratch. And it's kind of a terrible situation because the person that made the library often invested a huge amount of their time and effort to make it work. And then for me to decide it's just not even worth my time to read what they did, it seems like it's just a big waste of potential. But often that is the rational thing to do. And as I mentioned a moment ago, the other place you might see clarity falling by the wayside is when you deeply care about performance, it's very easy to take something that just needed non-pessimized and go eke out that last 5% performance. And you're moved into code golf territory, and now no one but you can understand it. So what is clarity? I think it is produced by taking an unfamiliar concept and mapping it onto something familiar in a way that's simple and concise. It provides an optimum path to get to the state of knowing. And you're carefully selecting information that steers the attention of the recipient into the right spot. The analogy I would give is the puzzle book Where's Waldo? There's a sea of little characters throughout the book, and they're all colorized to confuse your eyes. And you're hunting for that little guy in the red and white striped shirt. Now imagine how trivial it would be if you took and dropped the contrast of everybody except Waldo. That's clarity in action. Richard Feynman said, if you can't explain something in simple terms, then you don't understand it. And in discussing that quote with Colin, I think there's an even deeper insight here, and that's clarity is the duality of understanding. And the truth is, we don't understand but a fraction of what we think we understand. In practice, we can finish a task, but we don't necessarily understand it. You do it once, and don't get me wrong, you can do it again, right? And so sometimes that is the right thing, is just being able to do the task. But to understand it allows you to be able to be clear about it. People often approach sharing knowledge in one of two ways. Either a terse, go north, but no other directions, or they take a very exhaustive, throw the kitchen sink approach in which they don't know what's important. I find myself prone to fall in that latter camp on topics I get overexcited about, and I overwhelm my prospective new companion in a deluge of knowledge before they even took their first step. In the more terse approach, you're giving sparse information and told just go do the thing. The person may or may not understand the problem themselves, but they recognize it requires more work than they're willing to invest to produce a clear explanation. And additionally, when it's too terse, there's nothing to really go on, and so you're lost in the desert and have to find your own way. In the kitchen sink approach, the person providing the information likely doesn't really understand the problem, or like I said, could be overexcited, or they're unable to relate to the initial states of learning something. They have the curse of knowledge, and they can't map back to that time when they didn't understand. Fundamentally, the issue here is they did not distinguish what is important from what is not, so they just simply give you everything. And as the recipient, you have no way to know what's important, so you don't know what to pay attention to. Because you can't pay attention to something specific, or at least the right things, you can't get a footing in which you can find the lay of the landscape. Making it worse, we can hold precious few ideas in our head concurrently, so the flood of information is almost guaranteed to just go to waste. I highlighted willingness as an ingredient of clarity early on, and I think this is where most people falter. They want someone to go use their product, the library, whatever, or even just things they're sharing, but they're unwilling or unable to make themselves clear. And don't be wrong, it's not glamorous work, and I don't think it's intentional either. The kind of work is both painfully and it's humbling. You can take something that's done, it works, and try to clean it up so that it's clear, and watch a perception that you understood what you were doing just evaporate. I realize I only had a tenuous grasp of the thing I was trying to share with others, and it makes me have to retread that ground that I thought I was done with, and that can be very painful when you thought you were done. All right, so we've decided to strive for clarity, but there's a sea of information, and how do we winnow it down to something useful? Knowledge compression is similar to data compression. It's a step where you're down selecting what's worth keeping and what can be discarded. I like to think of it as a time to learn, if you will. So if it takes me 100 hours to solve a problem and it takes you 100 hours to understand what I did, why would you hire me? The compression was nil. But if instead you have a solid grasp within, say, 1 hour, now we have a 100-to-1 compression ratio, and it's worth keeping me around. Never forget that there is an economic cost benefit to your presence, and we sometimes forget to act accordingly. Another thing with knowledge compression is that it is lossy, like a JPEG or a Xerox. You have to pick and choose what's important, and that means you have to discard a lot of things. It provides a roadmap that if someone was to follow your path, they can get to the same place as you faster than it took you to get there. However, it's a lossy process. The knowledge of the dead ends, what did work, what didn't work, and why you made the choices you made, all of those obscure edge cases, they're still relevant in some scenarios. You're still the expert here, but for someone to collaborate with you, they rarely need to know any of that. Knowledge compression is meaningful for technical reviews. I normally have 5 to 8 engineers working for me, and accounting for overhead like meetings, mentoring, and so on. If my engineers don't deliver to me something at a minimum, like 10-to-1 knowledge compression, I can't even check their work with any measure of rigor at all. I would argue the minimum bar you should aim for is 40-to-1 in everything that you do. If you spent a week doing something, strive to explain a close copy of your understanding within an hour. Things can definitely be taken too far, from useful compression to just plain old compaction for no reason. And an example I'd give is I was working on a project quite some time ago. It was my first real software project at work, in fact. And I was doing spatial geometric work where I was finding physically connected items and how they connect to each other. And the original approach I'd made was to take a series of for loops and kind of do a linear transformation. It was maybe 400 lines or so of C#, right? And it wasn't an elegant solution, but it did work. You could read it, you could kind of follow what was happening. It was a very linear procedural type thing. I was learning LINQ and lambdas at the time, and I was very obsessed with how elegant they made my code look. And I ended up refactoring that method down into say 2 screens worth of a single massive lambda chain. And at the time, I thought this was glorious. I'd saved 300 lines of code, and I finally felt clever, like real programmers were. I felt elite. But 5 years on, I went back and looked at the code block, and I had no idea what I'd done to myself. I had to go back into the Git history and go look at the previous, larger, less compacted implementation. And it wasn't elegant, but it made perfect sense. And so we had to revert. So I'd love to give you some formula for success at improving clarity, but this is a very internal skill of perception and paying attention. And it takes both conscious effort and considerable practice. You need to think about the relative importance of your ideas and try to arrange them so that other people can understand them clearly, and test if the way that you compress them lands with other people. Conversation is exceptionally effective here. You're iteratively trying to explain something, and in real time, you're getting feedback if you're hitting the mark or if you're losing people. That gives you a chance to refine your approach and try to do better next time. In closing, I hope I've presented a strong case for working on clarity in everything that you do. The benefits are for you and everyone around you, and they make working together much more pleasant. Progress comes quicker, and it opens the door to more interesting problems in the future. Thank you for your time.
Hey, that was awesome, Jon. Thank you. So
Yeah, thanks for having me.
Floor for Q&A. Oop, 1 second, I can't hear you. Is your audio coming through? One moment. I can crank myself up a little bit. Here we go. I cannot hear Jon. 1 moment. I can hear some noise on your end. Jon, can you talk for me for a sec?
Yep, I'm here.
I'm hearing you now. Okay, cool. Awesome. Yeah, so can you expand on your 40-to-1 piece?
Yeah, so, I see this a lot. My background's in structural analysis, and I would have people present a set of stress notes for me, right? They're basically doing an analysis on some hardware. And, I would, like, where the idea came from is that I would assign, say, okay, go do this analysis and then write it up, and, we'll bring it back. And I go to review it, and it took me longer to understand what they had done than it would be to do it like twice over. And, I'd made a leg up because I told them what to do. I knew what was to be done. And, I think fundamentally and this applies for programming, analysis, anything at all really, is, this perception that I'm hired to be a programmer or I'm hired to be a structural engineer, and that's my job. Right. But the reality is we are working with other people, and the number one thing you're doing is communicating with them. And, with structural engineering, your number one job is to convince the world that you did it right. And similarly with programming, you need to make it run and compile, but what are you doing most of the time? You're reading, right?
Yeah.
And, I think we forget that a lot, that we'll make something that does work, it does compile, but it's illegible.
Right.
And so anyway, the 40-to-1 is, to me, just kind of a convenient rule of thumb. Like, if I can take my work week and turn it into something really useful for someone else, I mean, it's maybe a little bit arbitrary, but I really like it.
So in your traditional engineering background, do you have the equivalent of your C# case, where you go back months or years later and go, this makes no sense anymore?
Yeah. So, what we do in my background, like, you're going to do a structural analysis, and so you're going to go do a bunch of hand analysis, finite element analysis, something like this, and there's going to be like they call them tags, but basically you're something that was built maybe wrong, they misdrilled a hole, whatever, and so you have to go open these old structural analyses and say, okay, the hole's in the wrong spot. Is that okay? Can we use it?
Sure. Yep.
And so you get to see this a lot of times, and you come to learn, oh, this guy, man, we don't want to look at his notes because they're so painful. You'll spend days looking for how to go through it.
Yeah.
Or these other guys, it's like, man, I can just open it up and boom, I know right where to go.
Well, I think we talked about this previously. You said there's a time problem, right? If you don't spend, I think if you spend more than 100 hours, or it spends like the amount of time you spend learning as you did teaching, you end up kind kind of wasting the time you'd spent, right? If I'm bringing to my team, I did 100 hours of work, and I'm bringing to my team that 100 hours of work, but it takes me 100 hours to explain it, right? You wind up kind of wasting that time. That's kind of how you phrased it previously, and I think I really liked that phrasing. So let's see. Yeah. Yeah, I like that. So, how is this bridge even still standing? So,
right.
yeah. Right. So pair programming is an interesting one. I appreciate that, Ben. So if I'm pair programming and I've got two people working on something, so we've got effectively 200 hours of programmer time, presumably it does shorten the teaching time, but does that kind of work out?
I think it does, right? But there's always a
I'm
burden
not hearing you again.
for like the person doing the teaching.
John,
there's
we're
always a
not hearing you
burden,
again.
right? And when you practice being clear about things, you can accelerate that. But it how do I say this? So like there is a burden, right? And as I was trying to say in the talk a little bit is when you're trying to be clear about something, you actually have to be conscious about taking the effort to go do that. And sometimes it feels like it's faster to just go do it and just be to heck with the other person. But none of us are going to solve the 30 million line code problem by ourselves. And so you've got to bring people up with you, right? And I think we saw that a little bit with like Loris Crow's talk, right? He's saying like, I'd rather have 100 people that are have a imposter syndrome and they're a bit timid about it than somebody that's really good and an asshole.
Mm-hmm.
And so it's a burden we have to pay. And I think we sometimes don't want to pay it, but we need to, right? Because somebody taught us, we should be teaching other people.
Okay. Yeah, absolutely. Yep. Let's see. What else was on the list? Well, I'd love to hear more about, so I think you poked at writing a package manager ages ago for Odin. Where did that end up? What's next on your list?
So I ended up moving shortly after I kind of put it out for alpha, and it's kind of in suspended animation. I'm deciding what to do with it at the moment. Right now, it's there. It's not actively being used. And I'm contemplating, do I go and make it more just like a registry? Like maybe you could have a Discord bot that just, people showcase some cool library, it just grabs it and says, oh, here it is. Mm-hmm. The problem I was trying to solve was the information problem. Like, how do you find packages? And people have written some really cool stuff, and then Discord search isn't the best, and so you can't find things. My goal was not to go be NPM, right? I don't think Odin wants to have an NPM type package manager.
Sure.
And so yeah, I'm still trying to decide where to go with that to finish it up.
Well, you've talked about trying to get away from the NPM model. Really what you were saying was I want to avoid like dependency explosion, right? How do you constrain the packages that are on the system enough that you can give people good packages that aren't dependent on a million other things? Oh yeah. So
the thought there was, and these were unexplored thoughts, really, but at least had given some thought to it. Was maybe you could have kind of a pair of rules. One of them is a hard, like you can't have more than 25 dependencies in aggregate or something. I don't know. 25 even seems like a lot. Maybe 5. Who knows? And then the other part of the idea was maybe you can only nest 2 levels deep. Something like this where the trees stay really flat.
Okay.
You can have dependencies, but you're not having a bazillion of them. There's always ways to cheat that and get around it, but the goal is to like make it difficult. I saw a comment in the Twitch. Someone was asking, was it unofficial or official? It is definitely unofficial. Ginger Bill is definitely very concerned about the idea of having NPM show up again. And, I don't blame him, right? And it's not what I want to do. I want something that is helping with the discovery problem and really just the discovery problem.
Yep. So Ben's got a great question here. How did you get into programming from an engineering background?
So, okay. Early on, So in structural engineering, we use finite element analysis, and it's the program used most is called Nastran. It was written, gosh, in like I want to say the early 70s, and even today it still runs on text files. Okay, and these are big text files, hundreds of megs up to gigs. Right, it's not exactly an efficient format, but that's such as life. And I would be extracting the data to, and you're cutting things up really into little pieces. And, early on in my career, like I didn't know how to get the data out, and the visualization tools didn't really do you many favors. And so I was actually like manually copying and pasting out of a big text file. It'd take like days to do this. And, one of the guys down the road, or down an aisle rather, he like wrote me a little script, right? So I could get beam element forces out. And I'm like, wow, do I want to just be like a data monkey all my life, just copying and pasting things? Or do I want to like figure this out? And that set the seed. I want to take just a little tangent here. So when I first learned programming, it took me like 3 times to get into programming.
Oh yeah.
And, I had this presupposition, because people will tell me, oh, just go read a lot of code, and that's how you'll get, learn how to program. And, the problem there is kind of like I was talking about the talk is, you don't know what's salient in all that code first, right? And so there's tons of things, and like, it's obvious, like go start at main and go work your way down, but you don't know what's important when you don't know how to program.
Sure. Yep.
And, there's this piece of it, right? So it's hard to read code if you don't know how to program, but then also, and it took me a long time to come up to a conclusion, but, I originally believed that people who wrote, working code, like knew what they're doing completely. And then I had this presupposition, like, if I can't read that code, then I'll never be a programmer. And it like made me abandon ship multiple times. It was like 3 times before I actually learned how to program.
Yeah, it's one of those things that you eventually see enough code, and you go, maybe not everybody out there knows how to write code. It's a learning process.
Yeah.
I had a similar experience when I was doing like intro to programming way back when. I got into it with a little bit of C++, and then jumped out, and then got into Python, and then got back out, and it's a learning process, absolutely. So what eventually brought you back?
Back to programming?
Yeah.
So I think it was like 2012, maybe. I'm missing the year. I decided I really wanted to learn program for reals this time. And I ran across I think it's defunct now, but a site called 3D Buzz. And there's a guy, Nelson Lakay, I think he's actually lives somewhere up here, but he was teaching like an intro to C# course. And he really had a knack for giving you the right information at the right time, and make it salient in a way that you could actually go and do it. I think the first assignment, which was like the best assignment ever, was like you would make a little console vending machine, press 1 if you want to snack Snickers or something, I don't remember.
Sure.
And it got you past the idea of like, this is a Boolean, to now this is a program.
Right.
And there was still like a lot of OO in it, but it wasn't like obsessive the way that, it's really become today. And so it was pretty procedural, and it just, I don't know, it stuck for me.
Yeah. Yeah. Programming didn't really click for me until I sat down with a guy who has been doing it for ages and worked me through some C, some really procedural C for a job. And it went from, I sort of get it, to, no, I'm tracking properly, things are working. It can be very helpful to kind of see what code looks like if you just ignore all the design patterns and everything else, and just go, here's, top to bottom exactly what it's doing.
Yeah, absolutely.
Yeah. Yep. Well, awesome. Jon, it's been great having you on. I appreciate you giving us this talk and showing up. I think I'm going to move on here. 1 second.
No, thank you so much. I really appreciate it.
Yeah, absolutely. So a few minor technical issues did happen, but that is part of a new show. We've got plans for some follow-ups. We will hopefully get a schedule posted soon. I've got a few more, and I would love to get Billy on for one here soon, because we've got some slides queued up. But it has been awesome having everybody here. Thank you for showing up for Unwind.